The factorial is traditionally defined as n factorial is equal to n times n minus 1 all the way to 2 times 1. And this is valid for all positive integers including 0. But is there any way that we can extend this definition for real and complex number inputs? Well, we can, and it's called the gamma function. The main definition is given normally in terms of an integral. So consider the integral from 0 to infinity of e to the minus at dt. So you can evaluate this and you'll find that it's equal to 1 over a for all positive a. Now, we want to consider what happens if we take the nth derivative with respect to a on both sides. If you've worked with nth derivatives before, you know for specifically things related to polynomials and powers, factorial tends to appear in their formulas. So if we do this in the integral, due to Leibniz rule, this comes in as a partial. So we have partial of n over partial of a to the n e to the minus at dt. And then on the right side, it's just normal dn over dan, 1 over a. Now, to find these, let's consider some patterns. So if we start with 1 over a, then the first derivative is going to give us minus 1 over a squared. Then continuing, we get 2 over a cubed. Then minus 6 over a to the 4. And so this kind of gives us a pattern that the nth derivative is going to be minus 1 to the n times n factorial divided by a to the n plus 1. Similarly, for e to the minus at, again, this is with respect to a. So if we start with this, what we're going to get is that we have a minus t come out first, still proportional. Then we have minus t times minus t, that's just t squared, e to the minus at. Then we get minus t cubed, e to the minus at. And so this kind of gives us a general formula where it's going to be minus 1 to the n times t to the n e to the minus at. So we can just circle this out on the top. So now, plugging this in, what we're going to have is the integral from 0 to infinity, minus 1 to the n, t to the n, e to the minus at dt, and this is going to be equal to negative 1 to the n factorial, divided by a to the n plus 1. Now you can see that we can cancel this negative 1 to the n on both sides. And then from here, what we can do is plug in a is equal to 1. And then we get our formula. So the formula is n factorial, which Gauss specifically wanted to make separate from the traditional factorial, so that this is the one that's basically extended, which he called the pi function. So pi of n is equal to the integral from 0 to infinity of t to the n e to the minus t dt. However, this you'll find has a pole at negative 1, and what might sound nicer is to have a pole at 0. So what we typically use now and what's more popular is the gamma function, which is also valid for complex numbers. So I'm just going to use z now, which here is just n minus 1 factorial, or sorry, z minus 1 factorial, and this is equal to the integral from 0 to infinity of t to the z minus 1 e to the minus t dt. And so yeah, this is valid for real part of z greater than 0. More specifically, this is for absolute convergence. For example, putting in z is equal to I will still give you gamma of I, though that's conditionally convergent. From this, we can also find a functional equation similar to that from the factorial. So you can already see that if we consider gamma of z plus 1, then this is going to essentially be equal to z factorial, which is equal to z times z minus 1 factorial. And so we get that gamma of z plus 1 is equal to z times gamma of z, right? Now, this functional equation allows for analytical continuation to negative inputs as well. Basically, if you solve for gamma of z, so you have gamma of z is equal to gamma of z plus 1 over z, then you can also get negative results, though you'll find, and I'll just list these out now since it's important, with this involved, that the poles are going to be poles are going to be at z is equal to 0, minus 1, minus 2, and so on. So basically at 0 and the negative integers. So this is what we'll find the poles to be. But other than that, everything else works. Everything else can be plugged in. Along with this, if you want to consider some other integral representations with some substitutions, you can also get that gamma of z is equal to the integral from 0 to 1 of the natural log to the power of z minus 1 of 1 over t dt. And again, this is valid for the same stuff. This is now instead type 2 improper integral instead of type 1. And then for antiderivatives, we also have incomplete forms of the gamma function, specifically the upper. So for the upper incomplete gamma function, this is capital gamma. Ax is equal to the integral from x to infinity of t to the a minus 1 e to the minus t dt. And then the lower gamma function, lower incomplete gamma function, is lower gamma ax equal to the integral. Now it's from 0 to x t to the a minus 1 e to the minus t dt. And then along with this, what we can also have is alternative definitions, which also work directly for all other complex numbers except the poles. For example, we have two product representations. This one is given by Euler. Gamma of z is equal to 1 over z times the product, n is equal from 1 to infinity of 1 plus 1 over n to the z divided by 1 plus z over n. And then there's also the Weierstrass factorization, which is given as e to the minus Euler-Mascheroni constant z. Remember, Euler-Mascheroni constant is just basically the limit as n approaches infinity of the nth harmonic number minus ln of n, just to keep that in mind. So the Weierstrass factorization is e to the minus Euler-Mascheroni z over z times the product, n is equal from 1 to infinity of 1 plus z over n to the minus 1 times e to the z over n. And then interpreted as an inverse Laplace transform, this one is given as a reciprocal, but there's as a contour integral over a Hankel contour. We have that 1 over gamma of z is equal to 1 over 2 pi I times the contour integral e to the t dt over t to the z. In fact, the gamma function itself can also be interpreted as both a Mellin transform and a Laplace transform. Now I'm going to show some formulas which I see are sometimes useful in certain integral evaluations but aren't the typical identities. So first, we already saw from the proof of the main integral formula that the integral from 0 to infinity of t to the n e to the minus at dt is equal to n factorial over a to the n plus 1. And so this also means that the integral from 0 to infinity of t to the n minus 1 e to the minus at is equal to gamma of n over a to the n. And now this can already be shown that it's valid for n and a greater than 0, but then also by extension this is also valid if we had complex inputs for Re of n is greater than 0 and Re of a is greater than 0. Okay, and now another integral formula, which again I often use, is gamma of 1 over n. So this is just going to be the integral from 0 to infinity of t to the 1 over n minus 1 e to the minus t dt. Now we can do a substitution here. If we let u to be equal to t to the 1 over n, which also means that t is equal to u to the n, then dt is equal to n times u to the n minus 1 du. So now if we apply this, so we have gamma of 1 over n is equal to, so the n comes out, we have n times the integral from 0 to infinity of u to the 1 minus n e to the minus u to the n u to the n minus 1 du. So here you can see that these two cancel out, and so we get that gamma of 1 over n is equal to n times the integral from 0 to infinity of e to the minus u to the n du. So basically this is kind of given in terms of like a generalized Gaussian integral pretty much. And so this is also valid for, again, if we consider complex inputs, Re of n is greater than 0. Now let's consider some particular values of the gamma function, specifically those related to half. So if we have gamma of 1/2, well, we saw from a formula that I showed before, this is equal to 2 times the integral from 0 to infinity of e to the minus x squared dx, right? And this is just equal to, since the function is even, the integral from negative infinity to infinity of e to the minus x squared dx, and this is just the Gaussian integral, so this is equal to square root of pi. Another one to consider where we can use the functional equation is gamma of 3 over 2, also known as 1/2 factorial, where it sometimes might be stated. So this is just going to be, by the functional equation, 1 over 2 times gamma of 1 over 2, and that is of course just half of the Gaussian integral, so square root of pi over 2. Now how about negative results? So gamma of negative 1/2. Well, this can also be done using the functional equation. So this is just going to be the same as the gamma function at 1/2, divided by negative 1/2, which is just negative 2 times gamma of 1/2. So this is equal to negative 2 times the square root of pi. So you may notice that 1/2 gives us really nice values, and that's true that there aren't really any nice formulas in terms of known slightly more elementary constants than for other gamma values. So what we actually have are these closed formulas for gamma of 1/2 plus n, which you can kind of just see through pattern recognition, is 2n factorial over 4 to the n times n factorial times the square root of pi, or gamma of 1/2. And then there's also, for negatives, gamma of 1/2 minus n. This is just going to be the negative of the reciprocal of this pretty much. So we have negative 4 to the n times n factorial over 2n factorial times square root of pi. And this is for positive integers n. Okay, specifically positive integers, right? Because then the other ones just give you other gamma values. These ones stay as something over 2. However, for the other ones, there are some nice approximations because some of them can be interpreted in terms of elliptic integrals, and then there's stuff like the arithmetic geometric mean, right, which basically just alternates between the arithmetic mean, so a1 plus g1 over 2, and then square root of a1 g1, and then this goes basically infinite. So there's a nice relation to this and elliptic integrals. And then there's also the Stirling approximation, where we can restate, this is normally for factorial, but we can restate in terms of the gamma function as gamma of n plus 1 is asymptotically equal to the square root of 2 pi n times n over e to the n. So you can still get some value from other inputs, basically. For our first main identity that's used a lot, this is the reflection formula, which also allows for analytical continuation for negative inputs. So basically, we have gamma of z times gamma of 1 minus z, which is just equal to pi over sine of pi z, right? And so, for example, with this, we could also get gamma of minus 1/2, because we can treat this as gamma of 3/2 times gamma of, so 1 minus 3/2 gives you minus 1/2, which is going to be pi over sine of 3 pi over 2, that's just negative pi. And so then we get that gamma of minus 1/2 is equal to, and if we evaluate gamma of 3/2, we know that's square root of pi over 2. So it's going to be negative pi over square root of pi over 2, which is just equal to negative 2 pi over root pi, and then rationalizing, we get negative 2 square root of pi. Along with this, there is also the fact of a conjugate relationship. So basically, for the conjugate, if we have the conjugate of the gamma function, this is just equal to the gamma function of the conjugate, right? And so with this, you can also get hyperbolic forms of the reflection formula. For example, so we know that z times its conjugate is equal to the magnitude of z squared. So we have stuff like, for example, the gamma function at ni, where n is some integer, magnitude squared, this is equal to pi over n hyperbolic sine of pi n, right? Again, so this is for integers n. This is because of the relation to the circular and hyperbolic functions by imaginary arguments. Along with this, you can also get certain product and ratio relationships. For example, if we have gamma of 1 over 4 times gamma of 2 over 4 times gamma of 3 over 4, then this is equal to the square root of 2 pi cubed. And then as a ratio example, if we have gamma of 1 over 20 times gamma of 9 over 20 divided by gamma of 3 over 20 times gamma of 7 over 20, then we get a closed form here in terms of radicals. We have the fourth root of 5 times 1 plus root 5 all over 2. So the reflection formula is pretty useful. And the other well-known formula is called the duplication formula, which gives us something for gamma of 2z. So this is equal to 1 over the square root of 2 pi times 2 to the 2z minus 1/2 times gamma of z times gamma of z plus 1/2. And again, for example, this could be used to derive the value of gamma of 1/2. So we know that given this, so gamma of 2 times 1/2, that's just gamma of 1, which is equal to 1 over square root of 2 pi. And now 2 times 1/2 minus 1/2, that just gives us 1/2. So we have 2 to the 1/2, or square root of 2, times, there's our gamma of 1/2. And then again, gamma of 1/2 plus 1/2 is just gamma of 1. So we have some cancellations here, or simplifications. So this, as we know, is just 1. And then also square root of 2 here cancels. So then we get that gamma of 1/2, of course, has to be equal to square root of pi, as we checked before. Now, to be specific, this duplication formula, gamma of 2z, is actually a special case of a more general multiplication formula, where it's called Gauss's multiplication theorem, but it's basically for gamma of n times z. This is going to be 2 pi to the 1 minus z over 2, n to the nz minus 1/2 times, this is going to be a product of gammas, so we have gamma of z times gamma of z plus 1 over n, and this keeps going for gamma of z plus n minus 1 over n. Not entirely as useful, but it is a nice generalization. You probably use the duplication formula more. Before I end the video, I'm also going to talk about a related function to the gamma function, and this is called the beta function. So beta function is defined as b of xy, or b of yx, because this is symmetric, and it's equal to the integral from 0 to 1 of t to the x minus 1, 1 minus t to the y minus 1 dt. And its relation is that this is equal to gamma of x times gamma of y over gamma of x plus y. And again, since this is constructed basically by gamma functions, then we know this is valid for real part x greater than 0 if you're considering complex inputs, and real part y is greater than 0. Including with this, there is also a commonly used formula if you just do a trig sub with this. This also appears often, that this is also equal to 2 times the integral from 0 to pi over 2 of sine to the power of 2x minus 1 theta times cosine to the power of 2y minus 1 theta d theta. And then basically an improper version with an infinite interval, we also have the integral from 0 to infinity of t to the x minus 1 over 1 plus t to the x plus y dt. So this also appears quite often, and I'm probably going to use it in some future videos, I'm thinking. But yeah, it's nice to know this other function closely related to the gamma function. I will also mention, though not really go deep into this, that now that we have this explicit continuous form of the factorial, then basically derivatives are possible. So the gamma function, its derivative is actually proportional to itself. It's equal to gamma of x times this psi function, which is called the digamma function, which again, this is just pretty much defined to be the logarithmic derivative of the gamma function. And other than that, it goes a little bit deeper, and then subsequent derivatives, so nth derivatives, we say that's polygamma. And yeah, I'm not gonna really dive too deep into this, but maybe I might cover it in the future. It's just something to know. And one last thing before I forget is that the beta function also has an incomplete form, not used as much, but it's probably, I might use it in some videos. So this is basically, if you have b sub x of ab, then this is just the integral from 0 to x of t to the a minus 1 minus t to the b minus 1 dt. Okay. Anyways, I hope you enjoyed this video. The gamma function was pretty much, I think, the first special function that I learned about, and it's very interesting and it pops up everywhere. So it's really, really nice to know. And again, I also made this video because I'm going to be using it maybe for some other future videos. So yeah, I hope you enjoyed. If you did, click like and subscribe, and I'll see you in the next video.